The blood vessel is a conduit for blood flow, but its design emerges from its also being a complex machine to regulate shear stress on the vessel wall. It's one of the classic examples of how a complex design can arise from a simple regulatory process. And it's the reason why blood vessel networks, at least among vertebrates where we know something about them, conform roughly to Murray's law. There are two dimensions to this problem, one physiological and the other developmental. Once we've covered each, we can return to the original question: why do blood vessel networks conform to Murray's law? Let's start by looking at the physiology of shear stress regulation. Let's begin by reminding ourselves of the origin of shear stress in circular pipes. A parcel of blood flowing in the middle of a pipe will have a certain velocity, and because the blood has density, the moving parcel will have momentum. Through viscous forces, this momentum will be transferred through the blood to the vessel wall, which results in a parabolic velocity profile for the flowing blood. Blood velocity is maximized in the center of the vessel and falls to zero at the vessel wall. Just because the velocity of blood at the vessel wall is zero does not mean that the momentum has gone away, though. Remember that momentum is conserved. How it shows up at the vessel wall is as a force that pulls it in the direction of the blood flow. This is the shear stress, and it's usually symbolized with the Greek letter sigma. Shear stress on the vessel wall is increased by anything that steepens the velocity profile within a vessel, which means that anything that increases the average velocity of blood flow. For example, if the vessel radius stays the same, but the volume flow rate of blood through the vessel increases, this will increase the blood's average velocity, and this will make the velocity profile for blood within the vessel steeper. The result will be an increased shear stress on the vessel wall. By the same token, forcing the same volume flow rate through a narrower blood vessel will also steepen the velocity profile, and the result will be the same, an increased shear stress on the vessel wall. When this transfer of momentum imparts the shear stress to the vessel wall, the effect is to distort the endothelium. Specifically, the shear force pulls on the inside surface of the endothelial cell. Because the cell is attached on its other face to the basement membrane, the endothelial cell itself shears. If the shear stress is too great, it can actually pull the endothelial cells off the basement membrane, exposing the basement membrane to the flowing blood. Among other things, this can cause clotting and inflammation to appear at the point of separation. This is the origin of arterial vascular disease, so it's a matter of direct interest to the endothelial cell to ensure that the shear stress is not excessive. For other reasons, shear forces cannot get too small either. This has nothing to do with direct effects of low shear on the endothelial cell itself, but it does tend to produce the spontaneous formation of blood clots within the blood. We'll consider this when we talk about blood tissue in more detail a bit later. The basic point is that a well-functioning blood vessel is one in which the shear forces are maintained within certain limits, not too great, which would tend to impart physical damage to the endothelium, and not too small, which would tend to promote the formation of blood clots within the slow-moving blood. Within certain limits, this operates through active regulation of vessel diameter by the endothelial cells. The endothelium itself sits in close proximity to both the fibrous elements and the smooth muscle component of the tunica media. The shear force on the endothelium is regulated by the mediation of smooth muscle tension in the vessel. This, in turn, alters the vessel diameter, which, through altering the cross-section area of the vessel, alters the blood's velocity profile. Here's how that works. The vessel diameter is the result of a balance between two forces. The interior pressure, the blood pressure, pushes outward on the vessel wall, inflating it, increasing its diameter. As diameter increases, the fibrous elements of the tunica media stretch. Because they're elastic, the more they stretch, the more inward tension they put on the vessel. This is what we call passive tension. There's also a complement of active tension that arises from the tension of the smooth muscle band surrounding the fibrous protein. The diameter of the vessel will be where those two forces, tension and pressure, balance. If the endothelium experiences shear stresses that are too large, the endothelial cells begin to produce nitric oxide, which is a gaseous transmitter with the chemical formula NO. As an aside, this is not the anesthetic gas you get in the dentist's office. That's nitrous oxide, NO2. This is nitric oxide, NO. Nitric oxide is a powerful relaxer of smooth muscle tissue, and its production by the endothelial cells acts to relax the vascular smooth muscle. When the vascular smooth muscle relaxes, the vessel diameter expands until the pressure and tension forces come back into equilibrium. As the vessel expands, its cross-section area increases, the blood velocity decreases, and the shear forces operating on the endothelial cells ease. It works the other way as well. If the shear stresses are too small, the endothelial cells begin to produce a peptide hormone called endothelin. Unlike nitric oxide, endothelin is a powerful stimulant of smooth muscle tension. This increases the tension in the vessel wall, and the vessel radius will decline until there's a new balance of forces at a smaller vessel diameter. The reduction of vessel diameter reduces the vessel cross-section area, which increases the velocity of blood flowing in the vessel and increases the shear stress. The overall result of these opposing interactions between shear stress and smooth muscle tension is to regulate shear stress within fairly narrow limits. Shear stresses that are too high result in an increase of vessel diameter, which eases the shear stress. Shear stresses that are too low result in a decrease of vessel diameter, bringing shear stresses back up. This is all mediated by the ability of endothelial cells to sense the shear stresses they're experiencing and to take action, in this case the production and secretion of either nitric oxide or endothelin that adjust the shear stress to a level that, for lack of a better way to put it, is comfortable for the endothelial cells. This type of mediation is known as endotheliocentric regulation. This mechanism can be seen in operation in a phenomenon known as anomalous vasodilation. Vasodilation is the widening of a blood vessel, and it comes about through the relaxation of the vascular smooth muscle. The anomalous bit comes in because the people who discovered it were expecting an entirely different result. Here's their prediction. Imagine that we have a collection of cells that must have oxygen delivered to them at a certain rate, m.O2. This is supplied by a certain blood volume flow rate, V sub BL, driven by an arterial blood pressure, P sub A. What would happen if the arterial pressure, P sub A, was increased experimentally? The expected result will depend upon what we think is being regulated. Let's imagine, as it was long thought, that what's regulated is the molar flux of oxygen to the cells. If that is so, the effect of the increased arterial pressure will be to increase the volume flow rate of blood, and this in turn would lead to the over-delivery of oxygen to the tissues. If the tissues are regulating oxygen delivery, the logical response would be to restrict the anomalously high volume flow rate of blood, to bring it back down to the volume flow rate needed to deliver oxygen at the rate the cells are demanding. This should therefore elicit an increase in the tension of the vascular smooth muscle, which will reduce the vessel's radius, increasing its hydraulic resistance, which will bring the volume flow rate back down. What was found was actually just the opposite. The response to an increased arterial pressure was not the reduction of vessel radius, but its increase, hence the anomaly. The anomaly goes away if we imagine that what is being regulated is not oxygen delivery, but the shear stress experienced by the endothelial cells. Here, an increased arterial pressure results in an increased volume flow rate of blood, which results in an increase of the shear stress experienced by the vessel's walls. If what follows is not the increase of vascular smooth muscle tension, but its decrease, the vessel radius will increase, the blood velocity will be reduced, and the shear stress at the blood vessel wall will consequently be reduced. So, looked at from the perspective of the proper regulated property, namely shear stress, anomalous vasodilation does not appear so anomalous after all. So, it appears that the minute-to-minute operation of the vascular smooth muscle is organized around the regulation of shear stress by the endothelial cells. The bottom line is that everywhere in the vascular system, the endothelial cells will be continually adjusting the vascular smooth muscle so that the shear stress is regulated to a uniform value throughout. Remember this well. As we shall see, this is key to understanding why blood vessel networks conform to Murray's law. This physiological mechanism will be effective, but only within certain limits. At some point, even if the vascular smooth muscle tension has been reduced to zero, vessel diameter will be restricted by the tension in the fibrous elements of the tunica media. On the other hand, there will be some maximum tension that the vascular smooth muscle will be capable of. It follows that there will be some minimum diameter that the vessel will be capable of adjusting. Beyond these limits, this is where the second mechanism for adjusting blood vessel diameter and hence shear stress comes in.